Assalamu alaikum students. Welcome to our another online session for the course Digital Logic Design. My name is Ali Rahman and this session is specifically designed for the students of Software Engineering 3C. Well, in today's session we will be covering the universal gates. So let us first see the content which we will be focusing in our today's discussion. So as far as the universal gates are concerned, we have discussed in our previous session that the NAND gate and NOR gate are the two gates that are considered to be the universal gates. And why we ask them or call them the universal gates, because we can replicate all the other gates behavior by use of the NAND gate and NOR gate, which means that I can produce AND operation by use of NAND gate, I can produce OR operation by use of NAND gate, and I can produce the inversion or the NOT operation by use of the NAND gate. And similar is the case with the NOR gate. So in today's session, we will be focusing on all those concepts in order to implement other gates by use of the universal gates, and then at the end we will be implementing the exclusive OR gate by use of universal gates. Either we are taking the example of NAND gate or NOR gate. So to start our discussion, we are basically on chapter number 2, and let us discuss that how we're going to implement the AND operation, OR operation, and NOT operation by use of the NAND gate only. So for that purpose, we should know that how NAND gate operates and what is the property of NAND gate if we apply different set of inputs, and how the NAND gate reacts and produces the output for those different set of inputs. So if you remember that NAND is basically the reverse of AND operation, and symbolically we represent it as the logic symbol is similar to AND gate, but a difference is that there is an inversion or bubble at the output basically. So let's assume we've got two inputs X and Y and one output Z, and we can describe the Boolean function of Z as Z is equal to X and Y whole prime. Right, so now let us see the truth table. If you apply X and Y, what would be the value of Z? Since we know that the NAND operation is reverse of AND operation, so the output is basically inverted. Output of AND gate is inverted. So the output is 1, 1, 1 and 0. Right, so now let us see how we're going to implement the AND gate, OR gate and NOT gate. Starting with NOT gate. Then AND and OR. So the first example is NAND as NOT gate. Right, the second example would be NAND as AND gate. And the third example would be NAND as OR gate. Right, to start with NAND as NOT gate, so that NAND could produce the output of the NOT gate. And if you remember that NOT gate has a single input and single output, excuse me. But here NAND has two inputs. So how we're gonna replicate uh, this gate as a NOT gate? If you could observe that, if you observe these two combinations, the simple way to convert NAND as NOT gate is that if you observe these two combinations when both the inputs are same, what is the status of output on those combinations? So if you see that the inputs are 0 0, the output is 1, and when the inputs are 1 1, the output is 0. So the smart way to implement the NOT gate is if I could just short these two inputs so that when applied 0, 0 0 is applied at the input. In that particular case, this acts as the NOT gate. And we can also prove that by the Boolean function as well. For example, instead of y, I am also applying x dot x, which is basically equals to x by the Boolean algebra. So in that particular case, if you apply x at the input, we'll getting x prime at the output. So what we will do, we can also implement the NOT gate in different ways as well, but I think so this is sufficient. What we will do basically, we will use NAND gate, and we will just short these two inputs to implement NOT gate. So if I apply x here, now I'll get x prime at the output. How? Just consider the case, these two cases. If I apply 0 here, I will get 0 at this input and 0 at this input. Now at this combination, the output will be 1. And if I apply 1 here, 1 will be applied at this input, 1 will be applied at this input, and the output is 0. So here we can implement the NOT gate by simply short circuiting the two inputs, and now the NAND gate is acting as or behaving as the NOT gate or NOT operation. Now coming to the AND operation. And simple and straightforward, if you see the logic diagram of NAND gate here, if I use another inverter at the output, if I apply x here, y here, I will get here x prime, x into y prime, and after this inversion it would be x into y. Basically these inverters are cancelling each other's effects, so NAND will act as the AND gate. So if we have to use only the NAND gates only, and we know that we can implement NOT gate by using this setup, NAND and AND can be implemented simply as this is the first NAND gate, that has inputs x and y. Now we have to use this NOT operation, and we know that we can use NAND as NOT gate, so we will use this setup here. Another NAND gate, and we will short the inputs of this NAND gate, and now this basically acts as the AND gate, this setup. So here the output would be x dot y prime, and here at this point the output would be x dot y. Simple, straightforward. Well, now coming to the OR operation, and by the methodology, by the name, we can see that now we have to use the De Morgan theorem in order to implement the NAND as OR operation. And if you observe that the primary operation that we have constructed in NAND gate is basically the multiplication or the product operation, and then an inversion operation. So how we can use that in order to implement the OR gate, because in the OR gate the primary operation is the addition, the binary addition or the plus operation. So if you see that the expression of NAND gate is equal to x dot y prime, isn't it? So if we just open this expression to resolve the prime by using De Morgan theorem, we can say that this thing is equal to x prime or y prime. But for the OR operation, we require x and y other than x prime and y prime. What we will do is we will invert these inputs first. So if I take x prime into y prime whole prime, that would be equal to x double prime or y double prime. This will cancel out each other effect, and this will be equal to x plus y. So what we will do, simply we would have to invert the inputs first, and that's it. We've got the OR operation by the NAND gate. So we will use first of all two NAND gates to invert the inputs. This is the first NAND gate as NOT gate. This is the second NAND gate as NOT gate. So that if I apply x here, I will get x prime, and if I apply y here, I will get y prime. And if I construct the NAND operation between these two inputs, here now at this point I'm getting x prime dot y prime whole prime, which in fact is equal to x plus y. Right? So by this way we can implement the NOT gate, AND gate, and OR gate by use of NAND gates only. Okay, so I hope so the concepts are right now clear in your mind. Now let us see if we have to implement the NOT and OR operation by NOR gate only, then what would be the procedure? We are using basically the similar kind of procedure, and in that particular case we will be focusing on the behavior of the NOR gate first. So let us first see what is the behavior of the NOR gate so that we can implement the other gates as well. So as far as the NOR gate is concerned, This is the symbolic representation for the NOR gate. For example, I've got the inputs X and Y, and Z is the output. So Z is basically a function of X or Y whole prime. As far as the truth table is concerned, if you've got two inputs X, Y, and the output is Z, the output will be right. So now to start with our examples, how we're going to implement NOT gate, AND gate, and OR gate. Well, to start with, you can also observe that by observing the truth table, if both the inputs are same, the output is basically complemented. So we are using the same methodology just for the NAND gate. Similar is for the NOR gate to implement NOT gate. So what we would do is we will basically short circuiting these two inputs to produce the NOT operation. So if I apply X here, I would get X prime at the output. Now coming to the OR operation. So what we have to do is we have to invert the output of NOR gate. Simple and straightforward. For example, we've got a NOR gate. With two inputs, X and Y. We just have to invert the output. So here I will get X or Y prime, and this inverter will basically cancel the effect of X or this prime. So here I will get X or Y. So what we would do is basically we will use this setup here to replicate the NOT gate. So NOR as OR would be this is X, this is Y, and here another NOR gate, and here it is. It's done. Here we would get X or Y. Now coming to the AND operation. The AND operation can be seen as, if we see the expression of the NOR gate, that is equal to X or Y prime. So if we resolve this prime, so it would be X by De Morgan's theorem, it would be X prime into Y prime. Here we can see that we can produce the AND operation, but the issue is that we are getting the inputs inverted basically. So it's not X dot Y, it's basically X prime dot Y prime. So what we have to do is we have to invert the inputs first. So X or Y prime whole prime, this would be equal to X double prime into Y double prime, which is equal to X dot Y. So what we have to do is we will use two NOR gates for the inversion of X and Y. This is X, this is Y. Here I will get X prime, Y prime, and what we have to do is we have to NOR these two outputs as an input to the final NOR gate. This thing and this thing, and it's done. So here we have implemented the AND operation by use of NOR gate. Okay, so I hope so now the concepts are clear. Now let's go into the example basically to implement the exclusive OR gate basically. So let us first see the operation of exclusive OR gate and its Boolean function. Then we'll switch to the implementation by either NAND gate or NOR gate. So I will use NAND gate. You can also implement the exclusive OR gate by NOR gate also. So for the exclusive OR gate, if you remember that this is the symbolic representation for the exclusive OR gate. Oops. Let me erase that. X, Y, and Z is basically the function of X and Y, and it's represented as X exclusive OR Y, where X exclusive OR Y is equal to, and we have also proved that by the truth tables how we can extract Boolean functions by truth table either in a canonical or standard form of expression, which we've studied in our previous class. That is equal to X prime into Y or X into Y prime. So as far as the truth table is concerned, we've got X, we've got Y, and we've got Z as the output. So it's these are the combinations, and the output is 0, 1, 1, and 0. So if we implement this Boolean function by use of AND, OR, and NOT, and we can implement AND, OR, and NOT by use of NAND and NOR gates, we can implement this exclusive OR gate as well. So as far as the simple implementation or the plain implementation by primary gates is concerned, we are using two AND gates here with the input. The first is x prime, the second is y, and the second AND gate here with x as an input and y prime as an input. Okay, so what we would do is we would basically OR the output of these AND gates to produce Z. Right? So now let us focus on this thing implementation by the NAND gates only. So we know that how we'll implement NAND as AND. Basically, we are using two AND gates. So first of all, we will implement NAND as AND gate. So this is the first AND gate. This is the second AND gate. By use of NAND gates only. The inputs of first AND gate were x prime and y. So here I am using another NAND gate to invert x. Let me use some other ink so that you can differentiate the setup. So that was x. Here we would get x prime, and second input was y, if you remember that. And here in that particular case, the second gate, we've got x as a primary input. So either I can short this from here, or I can just label it as x. And the second input was complemented input. Let me redraw that. To represent the short operation between the inputs, and this is y, this is x. Now what we have to do is we have to construct the OR operation here between these two inputs. So we know that how we're going to implement the OR gate here. First of all, we have to invert the inputs of the OR gate. Let me use some other ink. This inverter is for the inversion of OR input basically, and we can see that we would cancel out some of the inversion operation to simplify our implementation. So this is the first not. This is the second knot, and what we would do is we would basically NAND these two inputs to produce C here, and we'll just simply interconnect in these lines, and that's it. This is the exclusive OR implementation by using the NAND gates only. And here you can see that, and in our starting lectures we have said that if number of inverters are in even quantity in any path on any circuit, they would cancel out each other effect. So we can see that this one will cancel this inverter's effect, and this one will cancel this inverter effect. And you can clearly see that if I apply one, if I'm getting one here, it would be inverted to 0, it would be inverted back to 1. So we don't have any use of these two inverters basically. So they are actually present in the circuit but are not contributing to the output basically. So what we would do is we would cancel these two inverters. This is cancelled with this one, and this inverter is cancelled with this one. So simply we have getting these two NAND gates, this NAND gate, and these two NAND gates. Okay, well, that was all for today's session. I hope so you will be able to implement any Boolean function by use of NAND and NOR gates. So similar, you can try this example by using use of the NOR gate also to understand the concept more efficiently. Till now, have a nice day. Take care.